Okay, welcome back to the trees slides. We're going to try and finish them up today. The last thing that we talked about before was traversals of trees, very similar to traversals of graphs, and I want to give you some practice with that. So take a moment, try out this example, and we will go from there. So give the order in which you would visit these nodes in this sample tree on the right in a post-order traversal, a pre-order traversal, an in-order traversal, and a breadth-first traversal. So give that a try, and then I will show you how I think about it. So when in doubt, you can always just code up the tree. And by the way, you should start from the root always, if it's a rooted tree. You can always just code up the tree and code up the algorithms and just have it print out when it gets visited. Or you could like draw a stack diagram, how things are moving, how the recursive calls are happening, and what still needs to happen. But I kind of do it a bit faster with the stack kind of in my mind, and I want to show you how I think about it so that you can practice this way maybe for a test. So here's how I think about post order. Post order, remember that post means it visits the root last. So it always goes, for a binary tree at least, it always goes left, right, root. That's the order in which it visits things for a post order traversal. So that is what I want to think about as I'm running it in my mind. So I'm starting with this tree rooted at A. I got to go left first. Left, right, then root. And again, now I'm at this subtree, and I'm making the same recursive calls, so it's always left, right, root. And so it looks like I visited D, then B. You see that? That's the order. And so I did the left, now it's time for the right. I gotta go, again, for this smaller tree, left, right, root. Left, okay, another smaller tree, left, right, root. So G, then E. There was nothing on the right, though. And again, we did the left, now it's time for right. F. Now it's time for root, C. And finally, we did the left, we did the right, time for root A. Does that make sense? That's how I think about post order. Let me just make sure I didn't make any silly mistakes yet. That looks correct. So yeah, that's post order. Pre-order is visit the root first, the root of your subtree. So it's always root left, right. Let's do pre-order. So root A, left. Okay, again, it's a smaller tree, so root B, left, right, then D. Nothing on the right. Okay, we did root, we did left, time for right. And it's a smaller tree, so root left, right. C, left, again, smaller tree, so root left, right, E and G. And then we did root, we did left, we did right, F. Okay? That is the pre-order traversal. And then in order, if it's a binary search tree, you can just like sort everything yourself if you want, but this one's a bit more complicated than that. Like these letters are not in binary search tree order. Smaller things aren't to the left, so you got to do the actual algorithm again. So in order, for a binary tree is the last option. It's okay, left, root, right. That's the last option of orderings, right? So the root's in the middle now. So it's left, root, right. Okay, so let's do left. Again, left, root, right. D, B, blank. D, B, that's what's getting visited. So we did left, now we do root, A, then we do right. Again, left, root, right. Again, left, root, right. G, E. And then we did left, we do root, C, we do right, F. I hope that's making more sense now. That's how I think about the stack and what still needs to be done in my mind. That's the idea. All right, let me double check all this. Looking good, looking good. And then breadth first is the easiest. That's just you read them off in level order. From left to right. So it's like that way, go that way, go that way, go that way. So that's easy. Oops. That is just A, B, C, D, E, F, G. Saved the easy one for last. Okay, so yell at me if you have any questions about this stuff, but those are the traversals that we talked about last time. Okay, based on traversals, you can do a lot of cool things. You can think of recursive algorithms essentially as a modified traversal. So maybe I should actually write that. You can think of recursive tree algorithms as modified traversals. That is a valid way of thinking about things. If that makes no sense, you don't have to worry about any of that, but sometimes it helps. So here is an example tree. Let's just get it ready. Here's the root, and it looks like this. It doesn't have to be a binary tree. It could be You could have as many children as it wants, just a normal tree. Nothing special. Could have like 5 children if it wanted to. But let me just do a binary tree because that's what we know and love. But the algorithm needs to be general enough to work for any kind of tree. So here is my tree. This is what it looks like. And here is Postorder for a arbitrary tree with arbitrary numbers of children. It's just do all the children recursively before you process the root of the subtree. So that's Postorder, the pseudocode for it. What you should do is what I want you to try now is try to adapt this code. Try to change it around a little bit. It's a recursive function. You have to make recursive calls to all your subtrees. Try to use that idea to compute the shortest distance from the root to a leaf. Okay? And you should return that distance. Okay? Your algorithm should return that distance. All right, this is an example I stole out of the book. This is just getting some practice with recursive functions on trees. So think about it this way. You're going to make a recursive call to the left, a recursive call to the right, and you need to use that recursive work, to compute the shortest distance from this original root to a leaf. So it's going to find the distance for these subtrees. So think of it that way, and then I'll talk about the way that I might approach this problem. Okay? So, starting from the root, I can make a recursive call to the left subtree and the right subtree. And remember that my game, what I'm trying to do is compute the shortest distance from a root to a leaf, where the distance is how many edges. Like this is supposed to be the shortest distance right here. 2 from the root, the original root. And in a recursive function, I get to assume that the smaller recursive calls on these smaller trees are going to do the right thing. Right? As long as I build up the answer, that's going to be true. So this should give me back 1, because from this root's perspective, the subtree's root, there's only one side we need to go down. Okay? If we go down to the left, then there's immediately a leaf. And so this recursive call should, for this example, return 1. We get to assume that it does. And then this recursive call, here's the leaf. It's 1, 2, 3 edges down. So that will give back 3. And in our recursive case, we need to look at this answer, and this answer, and try and give back the final answer for this original tree that's 1 bigger. And that's the hint, right? In each case, it's either 2 or 4, right? Length 2 or length 4, because your parent is 1 above you. So we're just going to pick the smaller side, because that's a shorter path to the bottom. So the answer up here should be 2. And that's the recursive case. Does that make sense? And then finally, you got to figure out the base case. It's like, how do you know, like this is going to make a left call, it's going to make a right call. How does this know, like, okay, it's going to add 1 to this side, so this side must have given back 0, yeah? It looks like when you have a leaf, the distance from the root of this subtree, which is the node itself, to a leaf, it is a leaf, is 0. There are no edges. So that is your base case, okay? So with that in mind, you can come up with an algorithm. Be like the minimum distance given a starting node v, which is usually the root of your tree, looks something like this. So if you're at a leaf, if v is a leaf, that's the base case, return 0. And then otherwise, for each child, because we're doing an arbitrary tree, maybe we had 3 subtrees. For each child, we're modifying this, remember. For each child, w of v, we need to make a recursive call. We need to call min_dist. That's the name of this silly function that I'm writing. Call min_dist on w, and remember the minimum. There's our recursive call, because we get to assume that it's going to do the right thing. It's going to give me back the minimum distance for that subtree, and save the min result. And then the answer, after doing that entire loop, is return that min plus 1. Because the root of this subtree is always 1 higher than each of these. So the minimum distance is the min path for the subtrees plus 1. Okay, did you get that? Does it make sense that you are kind of modifying Postorder If it doesn't, just think about it. It's a recursive problem. You're going to call on your subtrees and do work. Okay? Either way, you get the right answer. All right. So that is another question that I had for you, and hopefully that was fun. Now let's get on to some new topics. So first thing I want to say is a definition called something called a spanning tree. Okay? A spanning tree is when you have a graph already and you want to find a subgraph. Remember, a subgraph is just pick out some nodes, pick out some edges that you care about. That's a subgraph of an original graph. And what you want to do is, for a spanning tree, is you want to contain all the vertices, so you have to pick out every single vertex that's in your spanning tree. That's in your subgraph that becomes a spanning tree. And also, you want to make a tree out of the deal. So a spanning tree is, given a graph, pick out some of the edges that connect everybody up and form a tree, right? That is all it is. There are many options. Okay, so it's a connected, you got to start with a connected graph because you need to make a tree out of this. And remember that every tree must be connected. And you pick out all the vertices and some of the edges that connect it to make a tree. Okay, so here's a tree. It's like, okay, I'll pick out this edge, this edge, this edge, this edge, and this edge. That's all the vertices connected, and it's a tree. No loops or anything. And then here's another option. You go this way, this way, this way. All the edges are connected. It's, again, a tree. See how you can arrange it more tree-like? You could be like, boop, 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 boop. Something like that. So that's what a spanning tree is. Here's another option. Just got to connect all the vertices and make it a tree. Okay? So these are all subgraphs of the original graph, where the original graph is all the black plus the red. Okay, so that's what a spanning tree is. And you can think of this as, or it should be kind of clear that this is a useful thing to want to do. Like, I want to just pick out only the edges that help me get to somewhere else. I don't want to include any useless edges that I could have, like, there's another way to get to this edge anyway. I don't have to go straight from here to here. There's always a route, okay? I just want to find some path to get me there. I don't need multiple anymore. So it's just a minimum way to keep the graph connected. Okay? That's what a spanning tree is. And we're going to come up with an algorithm to create a spanning tree in a certain way in just a second. But before I get there, I want to talk about traversals of graphs again. Okay? That was the very first kind of traversal that we talked about in the last set of slides. So let's talk about these again in terms of trees, because we have just learned a lot of tree terminology. So graph traversals, when you're going through a graph, DFS, BFS, they look at the graph. They discover the entire graph, right? They visit every vertex somehow from some starting vertex. And once they visited a vertex, they never come back to it. They're not revisiting vertices. They just want to visit every place once, right? That's what a graph traversal does. So every graph traversal covers or creates a spanning tree. That's one way to create a spanning tree. Okay? There's an extra special way that I'll show you in a few slides to make an even cooler spanning tree. But every traversal you already know about creates a spanning tree. It's like, okay, here's the path that I took to discover, maybe from starting from this node, here's the path that I took to discover this node. Okay? That's the idea. So every traversal was creating a spanning tree. That's really cool. So let's quickly go back to the DFS and BFS slides just to prove that to you. Boop, boop, boop. Let's see. Do I have that? Trees. Darn, I don't have any graph slides open right now. So let me pause the video and be right back. Okay, I'm back. Let's talk about those again from this perspective. So let's go down here. Where were my traversals? Dun, dun, dun. I think it was down here. Yeah. So look at this. You see all those green edges? Dun, dun, dun. Of this graph? It's making a tree out of the deal. Does that make sense? That's breadth first search. This is depth first search. You see how it's not making any cycles. All these green edges are the order in which it finds all these nodes. It's a tree, secretly. Does that make sense? That is what's happening. And then remember that DFS was use a stack to get your way down to the bottom, go deep first, and breadth first search was go wide first. using a queue instead of a stack. Okay? So study these slides if you're a bit fuzzy on that, but that's what I wanted to tell you. I also talked about how depth first search stacks. I mean, you could have an explicit stack, but you can also make recursive calls to use the runtime function call stack, can't you? So DFS can actually, because it's using a stack, we can just make it a recursive algorithm instead and not actually have to use a stack data structure. We'll just implicitly use function calls to model a stack. Okay, so depth first search can be recursive, and let me show that to you. So here's another algorithm. Here is regular depth first search with an explicit stack, and then here's depth first search with a recursive way of doing things, and it's going to do the same exact thing. So let me show this to you. Same time complexity, does exactly the same stuff. It just uses an implicit stack instead of an explicit stack. Okay, that's the idea. So DFS starting at G, given a graph G starting at a vertex V, needs to look like this. The one thing you have to change is your visited variable, because we kept setting that in this loop body. It now has to be a global variable because we need to set it and have everybody see it because we're making a bunch of calls to the same function. It needs to be a global variable. That's the only change. So here's how you do it. So visited starts out empty, and then the function call stack starts out empty as well. So implicit stack now. So let's start at A, and this is our graph G, by the way. So let's start at A. So we're saying DFS G at the vertex A, and then we're off to the races. So if V is invisited, if it's not invisited, and it's not because visited is empty, so then we're going to visit A. So A was the first node that we saw. Okay, that's number one, and then we add it to our visited set, which is a global variable, and then for every adjacent vertex that is unvisited, trying to save ourselves some time there, so that's B, C, and E, those are adjacent to A, still unvisited, then we're going to call DFS on them in that order. Okay, so that's the first thing we do. So we call DFS on B. Does that make sense? So like we're calling DFS on A right now, and then we're going to call it on B, and also wait to call it on C and E from A as well. So now we're going to call it on B. So now we have another call to DFS, right? DFS on B instead. DFS on A has not yet returned. B is not visited yet, so we're going to visit it, add it to our visited set, and that's the second thing that we see. And then for every adjacent vertex that we haven't seen before, A we have seen, but D and F we have not, then we're going to call DFS on them. So we're going to call DFS on D and F. D first. So from B's DFS call, we're going to make another call to D. DFS on D, please. And we're going to have to remember to come back. Once we're done with this one, we have to also call DFS on if. Okay? Hopefully that's making some sense. So now we're in DFS G on D. We just called that. D has not been visited, so we visit it, add it to our visited set. It's the third thing that we see. And then we try and make recursive calls to DFS on all of its adjacent vertices, but its only adjacent vertex is B, and we've already visited it. So we're done working on D, and it gets popped off the stack. All the work is done for DFS on D, that returns. And we still have work to do for B, right? We visited D, we also need to recursively visit F. I hope that's making some sense. So we're going to call on F. DFS on F, please. Not visited, so let's visit it. It's the fourth thing that we see. And then, for every adjacent vertex that we have not yet seen, we've seen B, we haven't seen E yet, we're going to make that recursive call, okay? So now we're going to call it on E. That's the idea. And again, haven't visited it, so let's look at E. Let's go to all of its unvisited adjacent places and make a DFS recursive call, but we've seen A and F already. Oh, sorry, I forgot to add F. Excuse me. F came before E. There we go. F then E. Nobody else. E was the fifth thing that we saw. but everybody else we have seen. So no more recursive calls, we're done with this loop, and DFS on E returns back to the call of DFS on F. F has now also seen all of its children. It's called recursively on everybody that needed to call it on. So now DFS on F is done. The for loop's done, it returns. Now we're back to DFS on B. It has called DFS on all of its children now. It's called it on D and F. It's done. We've seen everybody there. Cool, huh? And then that means we're done with DFS on B. That loop's over. And finally, we're back to A. It needs to make a DFS call to C and E still, right? At least every one of its children that is unvisited. So technically, it only has to visit C now, right? So let's just do that. So A is going to make a recursive call to DFS on C. Let's go visit C now. And, well, we haven't seen it, so let's add it to our visited set. It's the 6th thing. And let's make a recursive call to every unvisited adjacent vertex. So looks like only G is left. So I'll make one last recursive call. Sorry, I forgot to add that to our visited set. And then we're going to take a look at G, right? Recursive call, visit it. We've seen it. It's the 7th thing that we saw. All of its vertices have been seen already. It's in the visited set, so we don't make any recursive calls. We're done with the loop. So we've visited G successfully, which means we visited C successfully. No more vertices to visit recursively. And then A also has no more vertices to visit recursively because everybody has been seen. So it pops itself off the stack. And that is the end of my call to DFS. And look at what just happened. I went from A to B to D, visited them in that order. Then I went from B to F, I visited in that order. F then visited E, like that. And then A visited C and G. That's the tree, the spanning tree that I drew, that I visited in that order, okay? So that's a tree out of the graph, no cycles. Isn't that fun? So that's one way that we visited every node. And so you can do DFS, you can do BFS, all these different ways to make a tree out of this graph, how we visit every nodes. The order in which we do that forms a tree. All right, so what I'd like you to do next is, with this in mind, draw the trees, okay? Do a BFS and a DFS on this graph. I've just copied it twice. It's the same graph. So draw the trees resulting from a traversal of the graph below, starting at vertex A, okay, using both BFS and DFS. So we'll do BFS and DFS on the same graph. And assume that when you make your recursive calls, you go, or when you add things to your stack and when you add things to your queue, you add them in alphabetical order, okay? Neighbors of a vertex are considered in alphabetical order. Okay, so try that. Draw those trees, and then I'll come and do it with you. So here's how I might do it. I'm going to do it a bit fast, so definitely go back to the algorithms if this was a bit confusing, but here's how I'll do it. So starting at A, let's do BFS. So we're going to visit all of the adjacent vertices in order. So think of your queue as implicit right now. So I'm going to visit B first, because that's in alphabetical order, through A. I'm going to visit E through A. I'm going to visit F through A. Yeah? And then each of these that we just visited, B first I guess, is going to try and visit its neighboring vertices that have not yet been visited, but we've already seen E and F. Same from E's perspective. We've already visited B and A. But from F's perspective, there's B to C, but then C and D still. Okay? So in that order, we're going to visit C and visit D through F. And that's the tree that we're going to draw out. Okay? Does that make sense, how I'm kind of implicitly doing the queue in my mind? That's kind of where I want to get you. So that's BFS. And then DFS is go as deep as you can first. So go from A and then, okay, the next place that I want to visit through A is the next thing in alphabetical order, so B. I have B, E, and F as options. We're going to go to B then, okay? And then now we're working at B from its perspective, because like this is our highest recursive call in the stack right now. So again, visit all the unvisited places, either implicitly through recursion or push them onto the stack, but we're going to make a recursive call, let's say, to E, because we have E and F as options, right? So let's go and visit E through B. And then there's nowhere to go that doesn't make a cycle, so we're done with E now. And now we're back looking at B. It still has places to go. And at E and F, let's go to F next in alphabetical order. And then we're looking at from F's perspective. That's the topmost recursive call. That's how I think about it in my mind. And so my options are go back to A, oh, we've already seen A, or go to C or D, again, alphabetical order. So we're going to C first. Bam. And so then we're now sitting at a recursive call from C's perspective. It needs to go and try all the unvisited places. Well, it can go back to F or down to D. We've already seen F, so it's going to go this way. In alphabetical order to D. That's going to be the order in which it visits its nodes, okay? And that's the tree that is going to be drawn out. That's the spanning tree of this graph. All right, please yell at me if you have any questions about that, but that's how I think about it. But again, you can always go back to the algorithm if you're stuck. Not a problem, okay? The final thing that I want to really get into right now, we have a few slides about them, is called minimum spanning trees. So let's say that we had more than just a regular graph. We had a graph with weights, okay? Graphs with numbers on their edges, like this one that we did for Dijkstra. So pretend we had graphs like this now that have weights. We might want to construct what's called a minimum spanning tree, okay? When you have a weighted graph, a minimum spanning tree is just a spanning tree, of course, but the spanning tree's weight along all the edges that you pick out to be in that spanning tree is no larger than any other spanning tree. So among all the possibilities of spanning trees, you're finding the smallest one, a minimum weight spanning tree. Okay, so that's a minimum spanning tree, or MST for short. And one algorithm that finds a minimum spanning tree is called Prim's algorithm. Okay, so I'm going to teach you Prim right now. So here is the intuition. The idea is that, okay, every vertex in the graph has to show up in the minimum spanning tree because we're taking every vertex somehow, right? That's what a minimum spanning tree is. So it doesn't matter which one we start with as long as we add the right edges, okay? So that's the first bit of intuition. And the second bit of intuition is, okay, what are the best edges to always add next to my spanning tree? Because you're going to pick out some, right? Take some edges and leave some out. You want a minimum spanning tree. So as long as you add the minimum edge possible each round, you're never going to do any better than that. Does that make sense? Because if you're adding the minimum edge, I mean, the total sum of edge weights is always going to be the smallest possible. So that's going to guarantee there isn't a better way to reach the next vertex you're trying to get to from your arbitrary starting point. Okay? So that is the intuition in a nutshell, and here is the actual algorithm that I'm going to go through with you. Okay? So again, you're given a graph with weights, and your output is a minimum spanning tree. So you're going to build up the tree T, your spanning tree from scratch, starting with the empty set. And the first thing you do is just arbitrarily pick a vertex in G. We need to add all of them eventually, so just take one, and we're going to add it to our set T. Okay, it's going to keep track of the nodes in our spanning tree that we've built up so far. All right, and so we have to add n minus 1 more vertices because there's n total in the graph G. So we have to add n minus 1 more to our spanning tree. Yeah. So it's got to do this loop n minus 1 times then. And here's what you do. You look at all the edges with one endpoint inside your set of things, inside your T so far, and one endpoint outside of T. I'll draw you that in a second. It's called the frontier. It's like some of this is inside of our spanning tree, like we've picked these edges and nodes so far, and then here's the rest of the graph, just moving around doing weird stuff. Consider all the nodes where one edge is in here and another edge is out here. So like you got that one maybe, that one maybe, that one maybe, that one maybe. Those are all edges that cross between here's your T and here's all of G. That's my best drawing of this. Okay, but I'll give you real examples in just a second. And what you do is, out of all these possibilities along this frontier, you add the minimum weight edge to your tree T. Okay, you're adding edges and vertices to it at the same time. So add that edge to T, which is going to add the vertex as well. Okay, and all right, that is the idea. Add the endpoint of E also not already in T. So that's what I just said. So you're adding the edge as well as the vertex that it was connected to. Okay? And so if you do this in this way, always picking the minimum weight edge, you're going to do the right thing. You're going to get a minimum spanning tree. This is one way to do it. All right? This is called Prim's algorithm. And so let me give you that as a real example. Remember that there's one inside, and one outside. That's kind of the key. So I'm going to show you the frontier now in picture form. So use Prim's algorithm to compute the minimum spanning tree for the weighted graph below. Start at vertex A, because it's arbitrary. We're going to just start at vertex A. So here's what I'm trying to say. Here's how you do Prim in a nutshell. So A is now in our spanning tree, that vertex. And now we have to pick an edge. So our frontier right now is, well, this guy and any edge that crosses over. We have all those 4 edges to consider right now to add to our minimum spanning tree that we're trying to build up. And what Prim does is it picks the smallest one. Picks the minimum weight one, where one side is in our current minimum spanning tree that we're building up and one side is outside. So it's this edge right here that's next. Do you see that? That's the 0 edge from A to D. So that's the next thing that we're adding to our minimum spanning tree. That's the minimum weight. And so now this together is the minimum spanning tree that we're building up. Slowly but surely it's getting bigger, one edge and one vertex at a time. So now our options of edges to add to this minimum spanning tree are this one, right? That one, this one, or this one. Which one's the minimum? We got 11, 9, and 8, and 10. We're going to pick the 8. That's always going to add the minimum run, okay? It's always going to make it as small as possible. So that's going to add this one next. And now we're at F. And now I can go a bit faster, I think. Look at all the possibilities where one edge, where every edge goes between something that's inside our current built up minimum spanning tree and one edge is outside. So, for example, this edge is now no longer possible to be added because it makes a cycle. It's no longer a tree. It's got to be one thing from a vertex inside of our minimum spanning tree and one that's outside. So like that's a possible edge to add. That's a possible edge to add. And we pick the minimum. So if you look at all your options, it looks like this 2 is the next possible one, right? That's the next minimum. It's the smallest one so far. So now the next node and edge that we add are this edge of weight 2 and H. So we bring that into our minimum spanning tree. And so what we've built up so far is, oops, I don't want that stray line. What we've built up so far is this minimum spanning tree. Okay, do you see the game that we're playing here? And so now among all the possibilities of one node inside the minimum spanning tree, one node outside, which one are we going to add? Well, it looks like we add this one right here. So we're going to add G next. Okay, and so I think you get the game now. The next minimum option is this 3 edge to E. The next minimum option appears to be I think we either have this 5 or this 7 next, right? So I'm pretty sure it's the 5 then. And then finally, the next minimum edge from something inside to something outside. So it's anything coming into here at this point. B is the last node that we have to add. It's this edge that gets us there. So we don't take the 7, of course. We're taking the 4. And that will construct successfully a minimum spanning tree. That's Prim's algorithm in a nutshell. And this is how we constructed the tree. Does that make sense? That is this algorithm written down in words. I think it's actually easier to think about in words, isn't it? Just drawing pictures. That's what Prim's algorithm means. Okay? So that was my example. I want you to try it for this one. Okay? Try it for this weighted graph. And this is a bit more complicated, but it's totally possible. You can also have negative weight edges. Who cares? You can also have fractional weight edges. Not a problem. So give this one a try. Compute the minimum spanning tree for this graph. Start at vertex A again. Okay? How do you add those edges using this algorithm? All right. So here we go. What are our options? This one, this one, and this one. I'm picking 0. You can have a 0 weight edge. Why not? So now this is our minimum spanning tree so far. Okay, what's the next one that we pick? It seems to be 0.5. It looks like 0.5 is the smallest option. Could add that one, could add that one, could add that one, could add that one, could add this one. But 0.5 is the smaller one. So I'll take this way to get to B. Fine. And then let's see what's next. We got -1. Oh shoot. No, that's the one I should have followed. Sorry. We gotta do -1 next. I didn't see that one yet. So those are our options, and -1 definitely wins out. So we're going this way. There we go. And again, there are no other negatives over here that we're connected to yet. So this one's gonna win. Going to I, and then again we're going straight to J. All those negative weights open up, and we need to follow those, right? And then the rest, let's see what we gotta do. I don't see any other negative weight edges that we could potentially follow. I just do see a 0.5, and that might be the smallest one now among all of our possible edges that we could add to our built-up minimum spanning tree. Okay, so I think that this one gets added next. And according to my notes at least, this is the right way to get there. So that should be the proper order. Now what's next? I could add one of these 4 nodes next, essentially, which is the one that I add with the smallest weight. It appears to be this one. I think the 1 is the smallest right now. So let's use the 1 to get there, to D. And then now I could go to either one of these, and I'm definitely going to C next, because this is the minimum weight, -4.1, of course. I'm using that route to get to C, not the 3 route, not the 2 route. No way. -4.1 route for me, please. And then I have H or F next, and getting to F is slightly easier. I can go by 3. And then finally, the only last node that I could add is H, and I have to follow this weight 4 edge. There's no getting around that. Okay? So that is the minimum spanning tree. Did you get that one? It's just a process. Just find which ones you could potentially add and then add it. That's how you do it. Okay, so that's Prim's algorithm all over again. And let me show you Prim in Racket, because why not? I assume you could follow this in C++, not too hard. Let me show you how to do it in Racket using this graph. And I'll prove to you that it's going to do the right thing and print out the right answer. Okay? So here is our graph G. Let's check our time, by the way. And I'm using it as an adjacency list. So for the node A in our graph, it could reach B by, it could reach B by 0.5. It could reach E by 0. It could reach C by 3. And so that's how I encode the graph. And then here is Prim. Okay? Prim on some graph G. That's a function. So let us build up our T, our minimum spanning tree T. I'll actually set it up into 2 different variables, the vertices of our minimum spanning tree and the edges of our minimum spanning tree for a reason. It's just easier that way to keep track of those separate things. And then n comes up a lot, so I save that. That's the size of the graph, of course. So vertices and edges are currently empty. I'm making a set of things that are empty. It's a mutable set, so I can change it in Racket. And then let's just arbitrarily take out A. Here's the first vertex in G. It's called A, and we're going to add it to our vertices set. So now A is sitting in our graph, or A is sitting in our minimum spanning tree T, and then n-1 times I'm going to do that loop. Okay, and I'm going to print out like which one am I considering right now. So here's what we got to do. We have to consider all the edges across that frontier, the boundary. And so I make a function that does that. It considers all the things across the boundary. Feel free to read this if you'd like. It is got to figure out, okay, what's on one side, what's on the other. It's a lot of code though, but take my word for it, that's what it's doing. And then we want the minimum edge across that boundary. So look at how I'm using functions to make my life easier. Like this was a difficult function, but once I have it, it's doing the right thing. So get the minimum edge across that boundary, and then add that edge to my T, and then also add it to the vertices, whichever one was not in the vertices of T already, okay? And then, yeah, that is my resulting minimum spanning tree, okay? So here's how you get the edges across the boundary. There's a lot to worry about there. And here's how you get the minimum edge across the boundary. You just kind of sort them and get the first one, okay? So feel free to look at this code. I'd be happy to explain it to you, but it's there's a lot going on there, so I don't want to get too far into it. So yeah, let's call Prim on G. So Racket. prim.racket. And so here it is. So the very first time it's going to, of course, add from A to E. That's the 0. And so we can actually make sure what I did was correct. So it adds this edge first. Then it adds E to G by -1. That's the next one that it adds. Cool. Then it adds G to I by -1. Yeah. I to J by -2, of course. And then A to B, D to E. Those are the next two minimum edges. And then C to D, F to J. So taking that one, of course, -4.1. F to J, that's the next smaller one. And then finally we have to do the G to H. That's the only last one possible. Okay? Yeah, and so those are the edges of the graph. That is the minimum spanning tree, and it looks like we did it right. Go us. Okay? So that is Prim's algorithm in Racket. Try it in C++ maybe. So that's the end of our trees slides, and I have a lab for you based on trees. So I'm going to go and record that video too, so go and watch that to get ready for your next lab. And then we're going to come back in the next lecture with a new topic. So I'll see you in one of those videos.